Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. So in previous video, we have been discussing the TDM model calibration. In previous video, the calibration was focused on finding the errors that are present in the network coding. I should say errors and approximations. And in this video, what we will do is we will focus on some in-depth analysis that is uses for calibration, and these are like fine-tuning the model such that it becomes calibrated. Also, even if the model is calibrated, the steps in this video is still done to understand the travel pattern that a TDM model is predicting. So in order to understand the travel pattern based on the TDM model, we still do all these processes even though the model is calibrated. So if a model is not calibrated, then the step we are going to discuss is going to help us to calibrate the model, and if the model is calibrated, or even if it's not calibrated, it will help us understand the travel pattern within the network. So let's get started. Let me choose a drawing pen here. So we will start from here. I should probably start a new paragraph after this one. So after the initial error correction process, which we discussed in our previous video, the next step is to look at the travel pattern in the TDM model itself. So there are um, two ways, or I should say two different techniques that are used to understand the travel pattern, and both of them are used on all projects. So it's not like we use one technique and the other one is skipped. They both go in hand together. So first one is called Screenline Analysis. There is an option to do Screenline Analysis within Transcad. However, we do not use the Transcad Screenline Analysis. Typically we just use the manual calculation. So what Screenline Analysis does is, let's say there are parallel routes. Let's say there are three parallel routes here, and the volume observed on this route is 100 vehicles, observed on this route is 50 vehicles, observed on this route is 50 vehicles. This is coming from the count. See. So this is what we observed in feed, and let's say in travel demand model, this volume changed to, this one is let's call it 50, and this one is 100, and this one is 50. So what travel demand model is doing is transferring 50 vehicles from here to here. Now there can be many reasons for this transfer. The link coding in this link may be wrong, the link coding in this link may be wrong. So what Screenline Analysis do is we look at the parallel routes and we look at sum of the volumes on those parallel routes. So the sum of volume on these three parallel route here observed is 200 vehicles, and the sum of volume on these three parallel routes here is 200 vehicles. So if the sum of volume on parallel routes are same, then that indicates that there is a issue with a routing choice, and there may be link or link issues or the routing issues. However, if the volume uh, observed on three parallel routes are not same as the count, then there may be issue with the trip generation or trip distribution. So that's what is mentioned here. So if the sum of volume on the parallel route is equal to what we are observing, then there is a issue with the routing, and we can look into the links on which the volumes are shifted to see if there are some coding error. So that is given in this one. So if the total volume across the screen line matches, this line is called screen line. However, we don't need to draw this in Transcat. We can just simply sum it up by eyeballing it. It's most likely an traffic assignment issue because the link attributes has been coded wrong. However, if we have these three links, the same links, and let's say in the counts we have 50, 150. So let's say we have 50, 150. However, let's say we observed 500 vehicles here and 50 vehicles here, and let's say 0 vehicles here. So total screen line volume observed here is 550, and total screen line volume observed here, this is the screen line count is 200. So when we have a situation where the vehicles, the trips and vehicles are not shifted among the routes, then most likely is a traffic generation or traffic distribution issue. So having an understanding of how the TDM is behaving, even if we are not gonna fix the errors, let's say we are not gonna fix the error or we did not find any issue, having an understanding that this route is getting overestimated and this route is getting underestimated will help us during post processing, where we will take into account that in TDM model somehow for some reason, for some unknown reason, this route was underestimated and this route was overestimated. So we will handle this situation in the post processing if we cannot handle it through calibration. So that's the screen line analysis. Then second important and very important one is select link analysis. Select link analysis is a feature within Transcad where when we run the select link analysis option, we can select a link and it tells us all the vehicles that are passing through this link. So it tells us how many vehicles came from this zone, how many vehicles came from this zone, how many vehicles came from this zone in a nice graph format, which is given on the figure on the next page. So let's say I have ran a select link analysis of this dark yellow or light orange color. Then the blue color shows the flow or the select link flows that is gonna pass through this dark yellow color. So we can see the majority of flows are coming from this node. Let me change the color here to green. So the majority of vehicles are coming from this node and they are going to here. A lot of them are going here, a little bit up, and a lot of them are going here. So usually they cannot end up at a corner, they have to end up in a zone. So I'm assuming they're gonna end up in some zones here. So what select link analysis tells us is if it tells us all the origin and destination zones from where this link is getting volume, and the width of this kind of new select link flows tells us how much volume is getting how much volume from this link is getting contributed to the selected link. So this is a very powerful, very important tool. We usually run the select link analysis for all the major roadways in the system. Even if we are calibrating or not calibrating, we always run the select link analysis just to understand where the vehicles are coming from and where vehicles are going. So select link analysis can help us with the calibration. Even without the calibration, it can help us understand the travel pattern for the major roadway or major locations. So we always run the select link analysis to understand how travel demand model is behaving. Now let's say the output of Selectlink analysis can help us to compare the TDM flow assignment to the OD observed. So what we can do is we can run the Selectlink analysis on TDM, and we can also run the Selectlink analysis on the uh, actual uh, actual platforms. For example, many OD platforms can let us run the Selectlink analysis based on the actual sample data. So many platforms which tracks the GPS based data can provide us a sample select link analysis, and we can visually compare how TDM select link analysis compares to the actual collected, which is collected in the field. But those are not 100% data, those are sample data which are provided by several GPS based flow processing platforms. So we can compare the select link with the actual data, which is again not full data but sample data. That's the one use of select link. Then use engineering judgment to consider if any adjustment to OD matrix is needed. Let's say we have observed that the this link is creating more volumes than what is expected. So by running the select link analysis, we can get an idea of which OD pairs are contributing to very high volume here and whether they are reasonable. If they are not reasonable, then we can do something called, let me change the color here to purple now, OD level correction. After all the correction are done and we are still not done with the calibration, and the last resort is to change the OD itself. So this is called OD level calibration, and this is one of the last resort we should be using. So OD level calibration, it's kind of difficult to write with a mouse. So OD level calibration is done when we tried everything and nothing worked, and then we what we are trying to do is we are trying to change the OD volumes such that we still maintain the sum of total production equal to sum of attraction, and we are trying to adjust the OD in the minimum possible way such that the link flows are more reasonable. And select link analysis is one way to kind of justify some of the OD level changes. One important thing to remember is whenever we are doing OD level calibration in existing, so this is our existing, and we are doing OD calibration, we must transfer this OD level calibration to future, because we have fundamentally changed the OD table. So future OD. A argument can be given that future AOD is independent of existing OD, so this calibration is not needed. Uh, however, in my personal opinion, that's not a good enough argument. If we are changing the OD level calibration and the travel demand models are based on the same assumptions, most engineers should change the future ODs as well. Then understand the major OD pairs and how traffic flows in the network. That's one of the biggest use of select link analysis, to understand how traffic flows in the network, and irrespective of calibration, we always run it for major roadway just to understand uh, how the traffic is flowing in the network. This understanding helps us to generate the final traffic volume, which we will discuss in the next video. That would be our last video on this chapter. After trying everything, what we are trying to hit is this TDM calibration target given by FHWA, Federal Highway Administration guidelines. So on freeway, we are trying to be within 5%. This is the acceptable range, within 7%, and this is the preferred range. So typically it's very difficult to hit the preferred. To be honest, we would be lucky to just hit the acceptable. So yes, if we can hit the preferred, and that would be really good, but acceptable is what we usually try to hit first. which is a little bit higher than preferred. If the model it all depends on how good the model is. If model is built in a very nice way and it has a lot of consideration, we might be able to hit the preferable. But the projects I have worked on, we were barely able to hit the acceptable, so we try to hit the acceptable thresholds. So these are the permitted error for different roadway types, and freeway has the less error because it's a high volume. So even a 7% error is a big number of trips that are deviating from counts. Next one is origin destination matrix estimation, famously known as ODME. So in transportation world, we will hear this word many times, called ODME. ODME. So what ODME is and why is it used? Before reading through the paragraph, let's look at some of the things. So travel demand model is not a rocket science. There are a lot of assumptions involved. It takes like 3 days to run, and not all the travel behavior, land use, there are so many things that goes in the transportation system. Not everything can be captured in travel demand model, especially if we are working with a very big travel demand model and we are trying to use it for a small region. The travel demand model can be can give the output which is far away from the counts. So TDM output, uh, let's say, is not only not equal to, is like far away from the counts. I don't know what's the symbol for far away. How, so TDM output, maybe less than, and greater than in some cases. So in many projects, TDM output are far away from the counts, and no matter what we do, we are not gonna match the counts. So we try our best to do the calibration, and if we are lucky, we at an early stage we figure out that TDM model we have received is kind of not gonna give us what we are looking for. So in the case where we have tried everything and nothing is working, we go for the last resort called ODME. ODME is a procedure within Transcad where we can force the Transcad to bring up an OD, like the name suggests, origin destination matrix estimation. So what it does, it throws away the, not throws away, it kind of generates its own OD just to match the counts. Now one thing to remember is number of elements within OD is usually higher than the number of elements within count. So there are infinite set of ODs that are gonna match the counts. So there are infinite set of origin destination when they are loaded on the system can match the counts. Out of this infinite set of ODs, like we have seen in the trip distribution, what we try to do is we try to pick the one which is the least deviating from TDM OD. So instead of throwing away the TDM OD, calling it garbage, what we do is we try to either use the TDM OD or we use the field collected OD from different sources, either TDM OD or field OD, and we try to use these two as something called base OD. So if we do not load the base OD, then there are infinite set of solution and Transcat will just give one solution that is gonna match the count. However, to improve the accuracy of our estimation, we usually provide the ODME procedure within TDM with either the TDM OD or the field OD as a base OD. So in this case, what Transcat tries to do is it tries to match the counts, but it also tries to keep the OD consistent. So it tries to keep the proportion of the elements within the base OD same as the proportion of element in the final OD. So there is some logic to madness when we are doing the ODME uh, by providing this base OD. So that's all the discussion that is provided here. One big point to note here is this is not a small occurrence. It happens on a lot of projects. So in a lot of projects, no matter what we do, on the calibration side, the models, because the models are very complicated, they cannot capture everything, and there are a lot of things that cannot be explained by TDM models. So for a lot of projects, what we do is we kind of try to we work hard to calibrate it as much as possible, and if the calibration cannot be done, then we have to kind of throw away most of the TDM and just take the just do the OD assignment. And after ODME, what we get is the new OD. So we get a new OD which has nothing to do with the TDM now, and then the new OD uh, which is deviating from TDM OD. So let's say for base year I have TDM OD here, and then I have new OD here. This is the adjustment that has been made for the existing year. Now what we do for horizon year is we have the TDM OD from horizon year, TDM OD for horizon year. Let's say this is base year. So we have the TDM OD for horizon year, then we transfer the adjustment. So for each element we transfer the adjustment to TDM OD in horizon year to develop an adjusted OD in horizon year. So what we are trying to do here is the same as what we are trying to do up here. It's called OD level calibration. We are trying to adjust the OD itself when everything has failed. So OD level calibration. This is the last resort, and once we run the ODME, it is gonna match the counts because there are infinite set of solutions, so it is always gonna match the count. So OD level calibration. The one thing to remember with ODME is to transfer the calibration to future years. So whatever we are doing, we need to transfer it. In the next section, we will discuss what does the calibration transfer means. Throughout this video and previous video, we looked at several ways of calibrating things and making changes to the existing network and existing ODs. So now since we have changed the existing network and existing OD, we need to transfer some of the calibration for future to account for the changes we are trying to make to the network. So future land developments, roadway configuration and traffic flow patterns are different than base year conditions. So in future the land developments are gonna change, roadway configuration are gonna change, and traffic flow pattern are gonna change. So engineering judgment should be used on how to transfer these calibrations, because the future model is built with having future in mind, existing model is built with having existing in mind, whereas the underlying principle in both existing and future is the same. So if we are changing something related to underlying principle in existing, then we should be changing that in future. However, if we are changing some characteristic of existing, which is going to be different in future, let's say the population is going to be different in the future. So if we are adjusting something related to which is very specific to existing, then the calibration may not need to be transferred for the future. So the guidance on whether to transfer calibration is provided below. So the first is do not transfer. We do not transfer the calibration that we make to the link speed, area types, functional class changes to TAZ attributes, which may be different and correct in horizon year. So for horizon year we go and manually check and whether they make sense, and if they make sense we do not change them. So most of the corrections we do in existing year, we do not transfer the corrections. However, there are several calibrations we do in existing, they need to be transferred for future year. Those are listed here. When we split a TAZ into smaller TAZs, then we are saying that there are developments within the TAZ that are significant enough to be separated out. So when we split a TAZ for consistency, the horizon year TAZ must be split in the same manner. We cannot just split one TAZ and transfer it. We have to manually split the second TAZ in horizon year as well. Splitting TAZ is never a fun and should be avoided. But if we are splitting a TAZ in existing, we should be splitting it in the future as well. Any changes to speed, capacity, and beta lookup table. If we are not happy with the lookup table are developed with a bigger reason in mind, and if we are not happy with the lookup table itself, that's a very big adjustment to the model. If we are changing anything with the lookup table or any parameters that are standard with user manual, then we must transfer those to future year as well. And not only transfer them, we must kind of get an agreement from the client before changing lookup tables or such drastic changes, because lookup table applies for the entire entire TDM model. So if we are changing some big things such as lookup tables, we should be transferring them to horizon year after getting approval from the client. Now the volume adjustment. So let's say I have a link here and my count on this volume is 500, and I ran TDM and the TDM uh, through a count as 400. So I know that link is getting underestimated by TDM by uh, TDM is missing 100 vehicles. So this kind of volume adjustment or the OD volume adjustment is transferred to the future based on the procedure which is described below. So V base is the volume in existing year based on TDM. Uh, this one is the volume based on TDM in horizon year, and then V base adjusted. Um, V base adjusted is what is the adjustment we made. So here we change the TDM to OD, so this will be our adjusted, and then V horizon adjusted. There are three ways of transferring this. I would say calibration or adjustments. So volume adjustment or mismatch is transferred from base year to future year using three methods. First is called difference method. It's usually used for smaller volumes. So usually for the vehicles number of, if the number of vehicles are less than 100 in base year, we usually use a difference method. So in difference method, we figure out how much adjustment we made. So let's say in existing the number was 500, we adjusted it to, in this example, let's say the TDM was 400 and we need to adjust it to 500. So in this, from the previous example, let's say the TDM threw out 400, but we know we need to adjust it to 500 because existing count or there is a reliable credibility that this link has 500 volumes. So what we do is uh, we have added plus 100 here. So in future volume, let's say TDM has forecasted 1100. Using difference method, what we will do is we will just add this difference which we have earlier. So we will add 100 more and call this 1200. This is the difference method adjustment. Very simple. Just figure out how much we added or subtracted from the TDM. So this is TDM versus actual. So and do the same thing for the future TDM. That's the difference method. Second method is the ratio method. Ratio method is used for larger numbers, usually greater than 100. So if we are working with larger numbers, let's say we are trying to adjust 1000 vehicles. So TDM said there are 1000 vehicles. In reality, there were only 900 vehicles. This is for base year. And assuming this is kind of uh, this is a roadway with a lot of lanes. So let's say in future year these are 2000 vehicles. So now if we use the difference method, we will end up with 1000 is changed to 900, and so 2000 will be changed to 1900. However, this 1900 is not that difference from 2000. So for bigger numbers, we use the ratio adjustment. So we looked at in what ratio did this got changed. So to change from 1000 to 900, what I needed was to multiply it with 0.9. So we're gonna multiply this with 0.9 and adjust this to 1800. So 1800 with ratio method, 1900 with difference method. That's very simple mathematics to adjust kind of volumes between the base year and future year using base difference method and ratio methods. In most of the cases, a combination of both is used. So for lower volume, uh, based on engineering judgment, for lower volume we use difference method, and for the higher volume we use ratio method. If you use ratio method for smaller volume, then it can give unrealistic results. So all those discussion is provided here, so we can read through them. So after TDM calibration is complete, horizon year models are run to generate horizon year traffic volumes. So let's say we are done with the model calibration. So we are done with base year model calibration, then calibration. Just calibration is enough. And what we are trying to do is, let's say we are done with horizon year model calibration transfer. So horizon year model calibration transfer. So we did some changes to base year and then we transfer them to horizon year. Now the next step will be to run the horizon year travel demand model. So after transferring the calibration, we run the model and get the horizon year flow volume, horizon year link flow. That's our output from the TDM. So at the end of this video or this step, what we got was horizon year link flow. So to recap, so far what we have done is we looked at the model development on how the travel demand models are developed, trip generation, trip distribution, model split, and traffic assignment. Then we looked at how the model is calibrated. So we looked at base year and horizon year. We looked at how these models are calibrated. So first we try to fix the errors, and then we try to understand the travel pattern, and then we try to adjust the travel pattern if possible. If everything fails, then we try to go with ODME. So any kind of calibration changes we do, if it's fixing errors, we do not transfer it. If it's like a big change, then we transfer it to the horizon year, which is horizon year model calibration transfer. After we are set with horizon year models, we run the horizon year models to get the link flow output for the horizon year or future year. Um, Horizon year is typically like 25 years ahead. So if I'm working on a project in 2022, my horizon year is most likely gonna be 2050. And then we get the link flows from the TDM model for horizon year, and then we post process it. There is entire video on how to post process this link flows. These link flows may not be reliable, they may be far off, because the TDM model has a lot of approximation and assumptions, and not every reality is captured with the TDM model. So we will look at how we're gonna utilize this link flow, how we're gonna utilize the existing counts, and how we're gonna utilize several data we have to come up with the final link flows. So at the end of this video, I just want to mention that once we run the TDM model, we just do not just take the link flows and then kind of call it good. We have to do some post processing. Also important to remember that most of the TDM model gives the link flow, so turning moment count still needs to be calculated. So if we are trying to code turning moment count in Transcat, then the Transcat itself will throw some weird results. So usually we get the results at link level, but now we need to change this link level flows into turning moment count, or turning moment volumes count is for existing. So there are a lot of post processing that is needed in Transcat, and it takes around like 10 to 20% of traffic, 20% of our time and resources. Post processing is usually done in Excel, and it's very tedious, but it's a very necessary step which we will cover in the next video. Thank you for joining in, and I will see in the next video.